Silicate minerals definition. Silicate minerals are a diverse group of minerals composed primarily of silicon and oxygen atoms, often combined with other elements such as aluminum, iron, magnesium, calcium, potassium, and sodium. They represent the largest and most abundant group of minerals on Earth's crust, constituting approximately 90% of its volume. This dominance underscores their paramount importance in geology, as they play crucial roles in rock formation, soil composition, and various geological processes. The structure of silicate minerals is based on the fundamental building block known as the silicon-oxygen tetrahedron, where one silicon atom is bonded to 4 oxygen atoms in a tetrahedral arrangement. This tetrahedral structure is the basic unit from which silicate minerals are constructed. Depending on the arrangement and bonding of these tetrahedra, silicate minerals are classified into several subgroups, including nesosilicates, sorosilicates, cyclosilicates, inosilicates, phyllosilicates, tectosilicates, and hybrid silicates. Nesosilicates, such as garnet, have isolated tetrahedra that are not connected to each other. Sorosilicates, like epidote, consist of pairs of tetrahedra that are connected by shared oxygen atoms. Cyclosilicates, exemplified by minerals such as tourmaline, form ring structures composed of linked tetrahedra. Inosilicates, such as pyroxenes and amphiboles, feature single or double chains of tetrahedra. Phyllosilicates, including minerals like micas and clay minerals, are characterized by sheets of tetrahedra bonded to sheets of other elements. Tectosilicates, such as quartz and feldspar, comprise three-dimensional networks of tetrahedra. Hybrid silicates, like zeolites, exhibit a combination of different structural arrangements. Silicate minerals exhibit a wide range of physical properties, including hardness, cleavage, color, luster, and transparency, which vary depending on their chemical composition and crystalline structure. They are integral components of various igneous, metamorphic, and sedimentary rocks, contributing to the diversity and complexity of Earth's crust. Additionally, silicate minerals have significant economic importance, as they are sources of valuable metals, gemstones, and industrial materials used in construction, manufacturing, and technology. Furthermore, silicate minerals play essential roles in environmental processes, such as chemical weathering, soil formation, and nutrient cycling. They influence the fertility and productivity of soils, affecting agricultural practices and ecosystems. Moreover, silicate minerals interact with atmospheric carbon dioxide through processes like chemical weathering, contributing to the regulation of Earth's climate over geological timescales. In summary, silicate minerals are fundamental constituents of Earth's crust, exhibiting diverse structures, properties, and roles in geological, economic, and environmental systems. Their study and understanding are crucial for unraveling the complexities of the Earth's past, present, and future. Silicate minerals characteristics. Silicate minerals are characterized by a variety of features that make them unique and distinguishable from other types of minerals. These characteristics encompass their chemical composition, crystalline structure, physical properties, occurrence, and significance in geological processes. Here's a detailed exploration of these aspects. Chemical composition. Silicate minerals are primarily composed of silicon Si and oxygen, O, atoms, forming silicon-oxygen tetrahedra as their fundamental building blocks. These tetrahedra may combine with other elements such as aluminum, iron, magnesium, calcium, potassium, and sodium to create the diverse range of silicate minerals observed in nature. Crystalline structure. Silicate minerals exhibit a wide array of crystalline structures based on the arrangement and bonding of silicon-oxygen tetrahedra. The structural diversity arises from variations in the sharing and linking of tetrahedra, leading to different mineral groups such as nesosilicates, sorosilicates, cyclosilicates, inosilicates, phyllosilicates, tectosilicates, and hybrid silicates. Physical properties. Silicate minerals possess a range of physical properties that vary depending on their chemical composition and crystalline structure. These properties include hardness, cleavage, fracture, color, luster, transparency, specific gravity, and streak. For instance, minerals like quartz are hard and have conchoidal fracture, while micas exhibit perfect basal cleavage and a characteristic sheet-like structure. Occurrence: silicate minerals are ubiquitous in Earth's crust, comprising approximately 90% of its volume. They occur in various geological environments, including igneous, metamorphic, and sedimentary rocks. Igneous rocks like granite and basalt contain abundant silicate minerals such as quartz, feldspar, and amphiboles. Metamorphic rocks like schist and gneiss may feature minerals like garnet, sillimanite, and staurolite. Additionally, sedimentary rocks like sandstone and shale often contain silicate minerals deposited by erosion and weathering processes. Significance in geological processes: silicate minerals play crucial roles in numerous geological processes that shape Earth's surface and interior. They contribute to the formation and alteration of rocks through processes like crystallization, metamorphism, and weathering. Silicate minerals are also involved in the cycling of elements within the Earth system, influencing phenomena such as plate tectonics, volcanism, and erosion. Furthermore, they serve as indicators of past environmental conditions and geological events, aiding in the reconstruction of Earth's history. Economic importance: silicate minerals have significant economic value due to their abundance and diverse applications. They serve as sources of essential metals, gemstones, and industrial materials used in construction, manufacturing, and technology. For example, quartz is utilized in the production of glass and electronics, while feldspar is employed in ceramics and pottery. Additionally, gemstones like garnet, tourmaline, and beryl are prized for their aesthetic appeal and commercial value. In essence, silicate minerals exhibit a rich array of characteristics that reflect their importance in geology, industry, and the natural environment. Their study and understanding are essential for unraveling the complexities of Earth's composition, history, and processes. Silicate minerals classification. The classification of silicate minerals is a comprehensive system that categorizes these minerals based on their chemical composition, crystalline structure, and bonding arrangements. Silicate minerals represent the largest and most abundant group of minerals on Earth's crust, encompassing a vast array of species with diverse properties and geological significance. Here's a detailed exploration of the classification of silicate minerals. Chemical composition. Silicate minerals are primarily composed of silicon Si and oxygen, O, atoms, forming the silicon-oxygen tetrahedron as their fundamental building block. The tetrahedra can combine with various cations, including aluminum, iron, magnesium, calcium, potassium, and sodium, to create different mineral species. Silicate minerals are classified into several chemical groups based on the arrangement of tetrahedral units and the types of cations present. Structural classification. Silicate minerals are further classified into several structural groups based on the arrangement and bonding of silicon-oxygen tetrahedra. These groups include nesosilicates. Nesosilicates have isolated tetrahedra that are not connected to each other. Examples include garnet and olivine. Sorosilicates. Sorosilicates consist of pairs of tetrahedra that are connected by shared oxygen atoms. Epidote and axonite are examples of sorosilicates. Cyclosilicates. Cyclosilicates form ring structures composed of linked tetrahedra. Common examples include tourmaline and beryl. Inosilicates. Inosilicates feature single or double chains of tetrahedra. Pyroxenes and amphiboles are prominent examples. Phyllosilicates. Phyllosilicates are characterized by sheets of tetrahedra bonded to sheets of other elements, typically aluminum. Micas and clay minerals belong to this group. Tectosilicates. Tectosilicates comprise three-dimensional networks of tetrahedra, forming frameworks that extend indefinitely. Quartz and feldspar are classic examples. Hybrid silicates. Hybrid silicates exhibit a combination of different structural arrangements. Zeolites are a notable example of this group. Subdivision based on chemical composition. Silicate minerals can also be subdivided into subgroups based on their specific chemical compositions. For instance, feldspars can be classified into potassium feldspar, sodium feldspar, and plagioclase feldspar based on the dominant cations present. Similarly, pyroxenes can be categorized as orthopyroxenes and clinopyroxenes depending on their crystal structure and composition. Accessory minerals. Some silicate minerals may occur as accessory minerals within larger rock formations rather than as major constituents. These minerals may have limited occurrence but can still play important roles in petrology, geochemistry, and mineralogy. Environmental and geological significance. The classification of silicate minerals is essential for understanding their roles in various geological processes, including rock formation, metamorphism, weathering, and soil development. Different silicate mineral groups exhibit distinct physical and chemical properties that influence their behavior in different geological environments. In summary, the classification of silicate minerals is a complex and multifaceted system that takes into account their chemical composition, structural arrangement, and geological significance. This classification framework provides valuable insights into the diversity, properties, and behavior of silicate minerals, contributing to our understanding of Earth's composition and processes. Silicate minerals examples. Silicate minerals encompass a vast array of species, each exhibiting unique chemical compositions, crystalline structures, and physical properties. As the most abundant group of minerals in Earth's crust, they play essential roles in geology, industry, and the natural environment. Here, we delve into a more extensive exploration of examples from various silicate mineral groups. Quartz. Quartz is one of the most abundant minerals in the Earth's crust and belongs to the tectosilicate group. It has a hexagonal crystal structure and is composed of silicon-oxygen tetrahedra linked in a three-dimensional framework. Quartz comes in a variety of colors and forms, including clear rock crystal, purple amethyst, yellow citron, and rose quartz. Feldspar. Feldspar is another common tectosilicate mineral group, comprising several species such as orthoclase, plagioclase, and microcline. These minerals are essential constituents of igneous rocks like granite and are also found in metamorphic and sedimentary rocks. Feldspars often exhibit a distinctive cleavage and can be white, pink, gray, or greenish in color. Mica. Mica minerals belong to the phyllosilicate group and are characterized by their sheet-like crystal structure. Common types of mica include muscovite, white or silvery, biotite, black or dark brown, and phlogopite, yellow-brown. Micas have excellent cleavage and are often used in electrical insulation, as well as in cosmetics and lubricants. Amphibole. Amphiboles are inosilicate minerals that form elongated prismatic crystals. They include minerals like hornblende, actinolite, and tremolite. Amphiboles are common constituents of igneous and metamorphic rocks, and their presence can indicate specific geological conditions during rock formation. Pyroxene. Pyroxenes are another group of inosilicate minerals commonly found in igneous and metamorphic rocks. Examples include minerals like augite, diopside, and enstatite. Pyroxenes have a monoclinic or orthorhombic crystal structure and typically exhibit dark green to black colors. Garnet. Garnet is a nesosilicate mineral known for its deep red color, although it can also occur in other hues such as green, orange, or brown. It has a complex chemical composition and crystalline structure, and different species include almandine, pyrope, and spessartine. Garnet is often used as a gemstone and abrasive material. Tourmaline. Tourmaline is a cyclosilicate mineral that forms prismatic crystals with striated surfaces. It comes in a variety of colors, including black, green, pink, and blue. Tourmaline is prized as a gemstone and is also used in various industrial applications. Zeolite. Zeolites are hybrid silicate minerals characterized by their porous structures and ability to absorb water and other molecules. They are often found in volcanic rocks and sedimentary deposits. Zeolites have numerous industrial applications, including water purification, catalysis, and gas adsorption. Epidote. Epidote is a sorosilicate mineral commonly found in metamorphic rocks. It typically occurs as green to yellow-green prismatic crystals and can exhibit strong pleochroism. Epidote is sometimes used as a gemstone or in lapidary work. Beryl. Beryl is a cyclosilicate mineral that includes several gemstone varieties, such as emerald, green, aquamarine, blue, and morganite, pink. It has a hexagonal crystal structure and is prized for its transparency and vibrant colors. These examples represent just a fraction of the diverse array of silicate minerals found in nature. Each species has its own unique characteristics and geological significance, contributing to the richness and complexity of Earth's mineralogical diversity.